Welcome to Lecture 9, Mathematical Induction, Section 2.2 of the text Elements of Modern Algebra by Gilbert and Gilbert. This is Dr. Gilbert Eyabi. 2.2 Mathematical Induction, or what is popularly known as the Principle of Mathematical Induction. Subsection 2.2.1 Proof by mathematical induction. Let Pn be a statement that we desire to prove true for every positive integer n. The proof consists of three things. Number one, we verify that P1 is true. That is the basis step, i.e., we have to prove that Pn is true for n equals 1. Step 2, induction hypothesis. We assume that Pk is true, i.e., Pn is true for some positive integer k. And step 3 is known as the inductive step. Using the assumption made above, that is the induction hypothesis, we verify that Pk plus 1 is true, i.e., the statement Pn is true for n equals k plus 1. If the steps 1, 2, and 3 are accounted for, then we conclude that the given statement Pn is true for every positive integer n. We call that the principle of mathematical induction, or simply PMI. Example: prove that the following statement is true for every n in n. N is the set of natural numbers, which is also the same as the set of positive integers. Or we can write it in the expanded form. Prove that this given statement right here is true for every positive integer. Proof: let Pn be the given statement. 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 2n minus 1, 2n plus 1 equals n over 2n plus 1 for every n in z plus. We call the entire statement Pn. Then we go through the three steps of the proof by the principle of mathematical induction. Step number 1, the basis step. We verify that the statement is true for n equals 1. This is the left-hand side and this is the right-hand side. So if n equals 1, what would the left-hand side be? If n equals 1, what would the right-hand side be? Would the left-hand side be equal to the right-hand side? We investigate. If n equals 1, then the left-hand side is 1 over 1 times 3, which is 1/3. The right-hand side is 1 over 2 times 1 plus 1. This is the right-hand side. It will be 1 divided by 2 times 1 plus 1, which is 1/3. So we have that the left-hand side equals the right-hand side, and therefore we can conclude that P1 is true. 1 down, 2 to go. That's the basis step. Step 2, induction hypothesis. For the induction hypothesis, you do not prove anything. We simply assume that the statement is true for n equals some positive integer k, i.e., we're saying that 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 2k minus 1, 2k plus 1 equals k over 2k plus 1. This is our induction hypothesis. We now proceed to step 3, the inductive step. This is where we verify that the statement is also true given the assumption above for n equals k plus 1. So the left-hand side is given as such, and the right-hand side becomes k plus 1 divided by 2 into k plus 1 plus 1. The numerator stays as k plus 1, and the denominator, you can expand this out. It gives us 2k plus 3. So to verify that the statement is true for n equals k plus 1, we have to verify that the left hand side equals k plus 1 divided by 2k plus 3. So we start off with the left hand side and show that it equals the right hand side. The left hand side equals, we go ahead and expand this out. The last term here is when n equals k plus 1, but before we get to n equals k plus 1, we go through n equals k. So if we expand out the left hand side a little, we would have 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 2k minus 1, 2k plus 1 plus 1 over all of this. So this is the very last term when n equals k plus 1, and this is the term before the last when n equals k. Why do I need this term? Because from my induction hypothesis, I already have the sum right up to the point when n equals k, and that sum is k divided by 2k plus 1. So going back to our problem, the sum right up to when n equals k by the induction hypothesis is k divided by 2k plus 1, plus the only thing that is left unaccounted for right now is the last term, and we leave it exactly as it is. So that gives us k over 2k plus 1 plus the last term becomes 1 divided by, in here we can expand this out and that should give us 2k plus 1, and we expand this out also and that should give us 2k plus 3. So by the induction hypothesis, I have k divided by 2k plus 1 plus 1 divided by 2k plus 1, 2k plus 3. We all know how to add fractions when the denominators are not the same. So we go ahead and multiply the first component in the numerator and the denominator by 2k plus 3 so that the denominators can be the same. If that happens, then the denominator would be 2k plus 1 times 2k plus 3, and the numerator will simply be the sum of the numerators of these two fractions. And the first one, expand this out, we have 2k squared plus 3k plus 1. We factorize out the numerator, and that gives us 2k plus 1 times k plus 1 divided by 2k plus 1 times 2k plus 3. We strike off 2k plus 1, 2k plus 1, and we are left with k plus 1 divided by 2k plus 3. Once more, what is our goal? We want to prove that Pn is true for n equals k plus 1, and we had concluded that to verify that step, we have to prove that the left-hand side equals k plus 1 divided by 2k plus 3. And this is where we are. K plus 1 divided by 2k plus 3. So that means pk plus 1 is true. We have shown steps 1, 2, and 3. And therefore we conclude by PMI, or the principle of mathematical induction, that Pn as defined above is true for every positive integer n. And that concludes our proof by mathematical induction. The basic step, induction hypothesis, and the inductive step. Before I present the next theorem, let's take this definition. Subsection 2.2.2, induction postulate. Let S be a subset of Z plus, i.e., S is a subset of the set of positive integers. If the number 1 is an element in S, And if for every element x in S, x plus 1 is always in S, then we say that a subset S, as a matter of fact, equals Z plus. We would call S an inductive set. As a matter of fact, Z plus, the set of positive integers, is the smallest inductive set. And not just the smallest inductive set, it is actually the intersection of all inductive sets. So, if I can find a subset of Z plus that is inductive, then that subset is nothing else but Z plus itself. So, if S is an inductive set and S is a subset of Z plus, then S has to be equal to Z plus. Keep this definition very carefully. We would come back to it. Subsection 2.2.3 theorem. The integer 1 is the least positive integer. Interesting. So this theorem simply says for every element x in Z plus, x is bigger than or equal to 1. I prefer to put it that way. There is no positive integer that is smaller than 1. Is that true? Does it even need a proof? Yes, it does. And we're going to prove it using the idea of an inductive set. Let S be the set of all elements in Z plus such that x is bigger than or equal to 1. Since all the elements in S are from Z plus, S is obviously a subset of Z plus. Now, all the elements in S are bigger than or equal to 1. That means the least element in S is 1. 1 is the least element in S. If I can successfully show that S is actually an inductive set, then since it is a subset of Z plus, it has to be equal to Z plus. And since 1 is the least element in S, 1 becomes the least element in Z plus, and I'm done. Easy strategy. Let us verify that S is actually an inductive set. Number 1, the number 1 is an element in S because 1 is greater than or equal to 1. So we're good. Number 2, suppose the element x is in S, we must show that x plus 1 is also an element in S. But x in S implies that x is greater than or equal to 1 by the definition of the set S. Now we know that the number 1 is bigger than or equal to 0, so I simply add x on both sides because x is a positive integer. Look at the properties of positive integers. So 1 is bigger than or equal to 0 implies that x plus 1 is bigger than or equal to x plus 0. But x plus 0 equals x because 0 is the additive identity in Z. So that means x plus 1 is bigger than or equal to x. But remember that x is an element in S. X is bigger than or equal to 1. And by transitivity, x plus 1 is bigger than or equal to 1. But what does it mean for x plus 1 to be bigger than or equal to 1? By the definition of S, that means x plus 1 is in S. We have shown that the number 1 is in S. We have shown that if I pick an element x at random in S, x plus 1 is an element in S. Therefore, by the induction postulate, S is actually Z plus. And since 1 is the least element in S, we can conclude that 1 is the least element in Z plus, and that concludes our proof. Let's take another example. Use the principle of mathematical induction to prove that the following statement is true for every positive integer n. N factorial is less than or equal to n to the n, and call that statement Pn. Basis step. We verify that the statement Pn is true for n equals 1. Left hand side, 1 factorial is simply 1. Right hand side, 1 raised to the power 1 is 1. The left hand side equals the right hand side, therefore we conclude that P1 is true. Induction hypothesis. Suppose that Pk is true, or assume that Pk is true. What does that mean? It means that k factorial is less than or equal to k raised to the power k for some positive integer k. Step 3, inductive step. We now verify that pk plus 1 is true, i.e., we have to verify that k plus 1 factorial is less than or equal to k plus 1 raised to the power k plus 1. In other words, in our statement Pn, we are replacing n with k plus 1. K plus 1 all factorial less than or equal to k plus 1 raised to the power k plus 1. How do we prove this? We start with the left hand side and use equalities and inequalities until we get the right hand side without cheating. Okay, let's do that. We start with the left hand side. K plus 1, all of these factorial, by the definition of factorial, equals k plus 1 times k factorial. Why did I do this? Because by the induction hypothesis, I already know that k factorial is less than or equal to k raised to the power k. So k plus 1 times k factorial is less than or equal to k plus 1 times k to the k by induction hypothesis. We did not touch k plus 1, so it stays, and the inequality is valid by the properties of positive integers. But what do I really want to get? I need k plus 1 raised to the power k plus 1. What do I have? I have k plus 1 times k raised to the power k. I do a few observations. K is a positive integer, so k is less than or equal to k plus 1 because 0 is less than or equal to 1. I can take exponent on both sides and still maintain the inequality sign by the properties of positive integers. So that means k to the k is less than or equal to k plus 1 raised to the power k. K is an element in Z plus, so we can do this. But what does that mean to our inequality? K to the k is less than or equal to k plus 1 raised to the power k. So all of these becomes less than or equal to, we have not yet touched k plus 1, so it stays, but k raised to the power k becomes less than or equal to k plus 1 to the k. From here, I have k plus 1 to the power 1 times k plus 1 to the power k. By rules of exponents, this is actually equal to k plus 1 raised to the power k plus 1. What have we done effectively? Effectively, we have shown that k plus 1 factorial is less than or equal to k plus 1 raised to the power k plus 1, and that is exactly what we stepped out to prove. Therefore, we can conclude that pk plus 1 is true. Hence, by the principle of mathematical induction, Pn is true for every positive integer n, and that concludes our proof. So far, we have seen the principle of mathematical induction. There is also the generalized proof by mathematical induction. In the generalized proof, the basis step does not necessarily have to start at the point 1. We simply verify that a statement is true for n equals a, where a is a finite number, any finite number. The induction hypothesis will be the same. We assume that a statement is true for n equals k, where our k is bigger than or equal to the number we started off with. And then we go ahead and verify the inductive step, which is also the same. We verify that a statement is true for n equals k plus 1. If these three hold, then we conclude that by the generalized mathematical induction, Pn is true for every positive integer n. It gets even more exciting with 2.2.5, proved by complete mathematical induction. In this case, the basis step, we prove that a statement is true for n equals some finite number a. A is an integer. Step 2, induction hypothesis. For any integer k, the statement is assumed to be true for every m in Z such that m is bigger than or equal to a but strictly less than k. And then we proceed to the inductive step. Using the assumption above, we prove or we verify that a statement is true for m equals k. If that happens, then we conclude that our statement as defined is true for every integer n. That is known as complete mathematical induction. A few problems for you. Problem number 1. Use the principle of generalized mathematical induction to prove that n cubed is strictly less than n factorial for every positive integer n bigger than or equal to 6. Here, your basis case would be when n equals 6, and you proceed from there. Problem number 2. Using the principle of mathematical induction, prove that summation I from 1 to n ai plus bi equals summation I 1 to n ai plus summation I 1 to n bi for every n in Z plus. In other words, prove that the summation of this sum equals the sum of the summations for every positive integer n. Number 2, prove that alpha times sigma I from 1 to n bi equals sigma I from 1 to n alpha bi for every positive integer n and alpha a real number. These are very simple properties we already know about the sigma notation, but this is abstract algebra and we expect you to be able to prove these common properties very easily. Thank you and God bless you.